Alrighty, number 9, we have two cars are driving and one car gets rear-ended by the other car. Originally, the mass of the car on the right is 1,200 kilograms and it was traveling at 14 meters per second. And the car on the left has a mass of 900 kilograms and was initially traveling at 20 meters per second. After the left car rear-ends the car on the right, they get stuck together and travel with the same velocity. The car crash takes 0.5 seconds. It says draw one of the bar charts below to represent this. Do the one that makes the most sense to you and matches the equation you will be using during the calculation section. Now, from the answer key here, I'm going to go ahead and show you how to do both. One thing to consider here is that the left side is the same either way. So I'm going to go ahead and do it here. So the left car, to calculate that momentum, we need to use its mass and velocity. So it has a mass of 900. So the momentum of my left car is 900 times the velocity is 20. And so I get a momentum of 18,000. And the right car initially, or I guess the whole time, has a mass of 1,200. And its velocity was 14. So the momentum of the right car is 16,800. All right, so to represent this, then I need to make sure that this one on the left is bigger because the momentum is bigger. And I'm just going to arbitrarily make it 3 tall. And one on the right is 16,800, so I'm going to make it 2 boxes tall. Because the momentum bar charts are meant to be general. They don't have to be exactly perfectly specific for this particular problem. I'm just looking for which one's bigger, which one's smaller, and which direction is it going? Is it positive or negative? All right, so when I have the momentum of both cars, then that means that on my momentum bar chart, diagram, I have to be able to add the 2 on the left to have it equal to the 1 on the right. So I don't know the velocity at the end, but I can tell you that if I have the one on the left with a height of 3 and I have the one on the right with a height of 2, that means that my total is going to have to be 5 tall. Now, the 3 and 2 and 5 don't actually mean anything in this problem, so I'm going to go ahead and erase them. But just as a general idea, I should see that the 2 on the left, if I add them together, I get approximately the height of the one on the right. Now, the left side of this is exactly the same for the other one. Now, when these two cars collide together, when I'm drawing them as two separate things, I have to be careful because although they have the same velocity, they do not have the same mass. And so because of that, their momentums will not be the same. And so if I think of it as, oh, maybe their velocity is 1, then that means the momentum of the left car will be 900 and the momentum of the right car would be 1,200. But that's not their velocity, but it gives me an idea for which one to draw bigger. So the right car is going to be bigger than the left car. So I'm going to go ahead and draw those. And again, I need to remember that if I add the 2 on the right, it needs to be equal to the 2 on the left. So I'm going to add these two together and make sure that it's equal to the other side. All right, so on the left side, I have a 3 and a 2 high, and on the right, I have 1.5 and 3.5. So those will add up together to be equal to 5. So that would be one example of how to do the momentum bar charts. Now it says write an equation to represent the momentum bar chart you created. So if you did the one on the left, you would say the momentum of the left car plus the momentum of the green car or the right car is going to be equal to the momentum of both put together. On the right-hand side, we would do the momentum of the left plus the momentum of the right is equal to the momentum of the left plus the momentum of the right. But now this makes it look like the lefts are the same and the rights are the same. So I'm going to go ahead and add a little, this is your starting for each of these. And these are your final momentums, just to make sure that we're keeping straight which one's initial and which one's final. Now, if you wanted to do this with numbers, that is also completely okay. And in fact, when we go ahead to substitute in to find that velocity for part C, that'll be the easiest way for us to do it. So I'm going to go ahead and do that. All right, so we calculated already that the left car had a momentum of 18,000 and the right car had a momentum of 16,800. So I went and put those in. So if I add those together, that'll give me 34,800, which will be equal to the momentum of both of them. And so I need to remember here to use the mass of both times the velocity of both. And this only works when this velocity is the same for both of them. So it only works when things are stuck together. And so now I just need to find the mass of both. So with a mass of 900 and 1200, I go ahead and put that in, and 900 plus 1200 is 2100. Now I've got an equation that I can solve for the velocity. So because it's 2100 times the velocity, I'm going to go ahead and divide by 2100 because that's the opposite of the multiplication. And I get a velocity of 16.57 meters per second. So now I'm going to do it using the other equation and show you that it comes out exactly the same. So using this other equation, so we already had those starting momentums, so I plugged those in. And then the issue is we don't know the velocity after the collision. So I end up with 900 times some velocity that I don't know and 1200 times some velocity that I don't know. But then what do I do with that? Well, one thing to remember is if you have 2x plus 3x, that'll be equal to 5x. And although the v's are not x's, the math is the same. So 900v plus 1200v is going to give you 2100v. And 18,000 plus 16,800 will give you the 34,800. And now we're back to exactly what it was like over here. So all we need to do is divide by 2100 on both sides, and we get the same velocity of 16.57 meters per second. So for part D and E, we're trying to find the change in velocity, and change in velocity is just final minus initial velocity. So we need to look at how fast was it going at the end and subtract that from how fast it was going at the beginning. And so for both of these cars, they were both had the same final velocity of 16.57 because that's what we just figured out right here in part C. So we go ahead and plug those into the equation, and then we just need to look back up at the beginning of the problem and figure out what those initial velocities were. Well, the initial velocity of the left car was 20 meters per second. So we get 16.57 minus 20, which means we will get a negative 3.43 meters per second. And in case you're worried about that negative, it's okay. It just means that it slowed down. So it was going 20 meters per second. Now it's going 16.57. That means you slowed down by 3.43. So that's fine. The other car was initially going at 14 meters per second. So that means that that car sped up by 2.57 meters per second. All right, and moving on, we've got what was the change in momentum of the left car. So to find the change in momentum of the left car, I would need to do it one of two ways. You can do it by doing your mass times the change in velocity, which is handy because we just did that. Or you can figure out the momentum of the car after the collision and subtract that from the initial momentum of the car. So I'm going to do it the first way first. So my change in momentum is equal to the mass of my car, which was 900, times the change in velocity of the car, which was this negative 3.43 meters per second. And so therefore my change in momentum is going to be equal to 3,085.71. Or I could do it the other way, and I could do final minus initial. And so here I'm doing my change in momentum is equal to my final momentum minus my initial, but I don't know my final yet, so I'm going to have to figure that out. Minus my initial, which we already figured out was 18,000. So my change in momentum is going to be 900. 900 times 16.57 gives me 14,914.28, and I'll subtract from that the initial, and I will get a change in momentum of negative 3085.7, which is great news because I need to be able to do this problem either way and get exactly the same answer. All right, so I get a negative 3,000 and stuff both ways. Now I can do this exactly the same way for the right car if I needed to do it for the right car, but it's not asking me to do that. So the next thing it says is how much force did the left car push on the right car with? And so this one, you need to remember that impulse is equal to your change in momentum, or you can remember that force times time is equal to your mass times your change in velocity. Now, the important thing here is if I use the car on the left, I need to use the car on the left for both the mass and for the change in velocity. And so I will get the force times time is equal to the mass of my left car, which is 900, times the change in velocity of my left car, which is the negative 3.43. And when I multiply that together, I get 3,085.71, which happens to also be the change in momentum that we just got here. So that's good. We get the same thing twice. And then force and then time, it said in the problem, was a half second. So that's 0.5. And I just need to solve for force. And the force that I get is going to be 6,171.4 newtons. Now, if I do this the same way and I use the right car for the mass and the right car for the change in velocity, I will get exactly the same answer as long as I've been keeping all of the digits in my calculator. If you round it at all, you will get a very slightly different answer, but that's okay. So I went ahead and did it the other way with a massive 1200 and a velocity of 2.57. And again, indeed, I got exactly the same force. And this is important because regardless of what force you get here, the two cars must always push on each other with exactly the same force for exactly the same time. That's one of Newton's laws. And that means that the answer for H is whatever you got for G. So the answer for H is also 6,171.4 newtons. If you have any questions, let me know.